Welcome to Why Stuff Happens. I am Hope. Let's find out together.
Let's dive in.
Picture this. You're in the lobby of an office building,
Right.
and you're about to walk into an incredibly important meeting.
Oh no, I can already see where this is going.
Right, maybe it's a job interview, or a pitch you've been preparing for months, or honestly, maybe you're just finally relaxing on your couch after a brutally long week wearing like your favorite, most comfortable bright red t-shirt.
Yeah, the one you really don't want to ruin.
Exactly. So you reach for a glass of ice-cold, perfectly clear water, and then, well, disaster strikes. You misjudge the distance by a fraction of an inch, your hand slips, and you splash water right onto the front of your shirt.
Yep. It's just a universally humbling experience.
It really is. You look down, and instantly that wet spot isn't just damp. It appears so much darker than the rest of the fabric. I mean, it stands out like a neon sign broadcasting your clumsiness to the entire world.
And usually the immediate reaction is, a mild panic. You're frantically searching for the nearest restroom hand dryer.
Or doing that desperate attempt to dab it away with a napkin.
Which, as we all know, only makes the dark spot spread and look so much worse.
Oh, the napkin dab is always a fatal mistake.
Uh-huh.
But if you can force yourself to, stop panicking and think about it for just a second,
Yeah.
there is this central everyday absurdity to this entire situation.
There really is, yeah.
Because the water you just spilled is completely clear. I mean, it is entirely colorless. You could look right through it in the glass.
Right, it's transparent.
And the dye of your red shirt hasn't magically changed its chemical composition in the 3 seconds since the spill, right?
Yeah.
So how on earth can clear, transparent water make a colored material look distinctly, undeniably darker?
It feels like a glitch in the matrix when you really stop to dissect it. I mean, you add a perfectly clear substance to a brightly colored substance, and instead of diluting the color or washing it out, you get this darker, deeper, heavier version of it.
Yeah, exactly. Our brains instantly tell us, wet equals dark.
But the physics behind why wet equals dark is completely counterintuitive to how we normally think about the physical world.
You add a clear liquid to a colorful shirt, and it gets darker. To understand this glitch, we have to realize that our entire concept of what a surface is and what dry actually means is essentially, well, an optical illusion.
It is, yeah. It's a total illusion.
Welcome to this special deep dive. Today we're going to serve as your shortcut to being well-informed about the hidden science hiding in plain sight. We are going completely down the rabbit hole to decode the optical physics behind your clumsy spills.
And we really do have to build this from the ground up.
Okay, let's do it.
Because to solve the mystery of the dark spot, we have to completely rethink how light behaves when it slams into a physical object and how our eyes interpret that collision.
So let's start with the absolute baseline. Before we can even begin to understand why the wet spot on that red shirt is dark, we need to understand why the dry shirt looks red in the first place.
Right.
Let's talk about the nature of how we actually see anything in the room around us.
So the foundational concept here, and this is something we often just take for granted, is that an object's appearance entirely depends on the light that manages to survive a journey and reach our eyes.
Right, because we have this deep-seated psychological tendency to think of color as an inherent fixed property of an object.
Exactly. We point and say, that shirt is red, or that car is blue. But from the standpoint of optical physics, the shirt itself isn't generating redness. It isn't glowing.
Yeah, it's not a light bulb.
Right. Its appearance is entirely the result of a highly specific, chaotic interaction with the ambient light around it.
So if I'm standing in a completely pitch black room wearing my red shirt, the shirt doesn't actually have a color.
No, not at all.
It's just a piece of fabric waiting for light to interact with it.
Precisely. To understand what happens when you turn the lights on, we need to define 3 fundamental behaviors of light when it hits matter.
Okay, what are they?
Reflection, scattering, and absorption.
Got it.
Mm-hmm.
I always like to visualize these concepts because the invisible waves of electromagnetism can get a little abstract.
We definitely can.
So I picture light as a stream of millions of tiny glowing ping pong balls being fired out of the light bulb in my ceiling.
That's a classic and honestly highly effective way to model it. It perfectly represents photons, which are individual packets of light energy.
Okay, sweet.
So let's take your ping pong balls. What happens when they hit a surface? The first behavior is reflection, specifically specular reflection.
Specular reflection, meaning like a mirror.
Exactly. If you fire those ping pong balls at a perfectly smooth, flat, hard surface, like a polished bathroom mirror, they
Right.
bounce off in a very organized, predictable way.
Right.
They hit the mirror, and they bounce directly back at you, or bounce away at the exact same angle they came in.
Right, like bouncing a basketball perfectly on a flat gymnasium floor. It comes right back to your hand.
Perfect analogy. But most things in the world aren't perfectly polished mirrors. Which brings us to the second behavior, scattering.
Okay, scat.
If you throw your ping pong balls at a wall made of, say, jagged, uneven, crushed rocks, they don't bounce back in a neat line.
No, they'd go flying everywhere.
Exactly. They hit the angled faces of the rocks and ricochet everywhere, up, down, sideways, into each other. It is a disorganized, chaotic reflection.
And then there's the third behavior, which I imagine is like throwing those ping pong balls into a giant deep pit of wet mud.
Absorption, yes, exactly. The balls hit the mud, they stick, and they stop moving entirely.
They just die in the mud.
Right, their kinetic energy is transferred into the mud. In terms of light, when a photon is absorbed by a material, it doesn't bounce back at all.
So it's just gone.
Its electromagnetic energy is soaked up by the atoms of the material, and that usually causes those atoms to vibrate just a tiny bit faster.
Oh, wait, so we perceive that microscopic vibration as heat.
Yes, a tiny imperceptible amount of heat.
Okay, so we have the flat wall bouncing them back, the jagged rocks scattering them everywhere, and the mud pit swallowing them whole.
Perfect summary.
How does this
Well said.
translate to the red dye in my shirt?
Well, white light, whether it's sunlight streaming through the window or the fluorescent tubes in that office lobby you're standing in, it contains all the visible colors of the spectrum blended together.
Right, the whole rainbow.
It's a stream of ping pong balls of all different wavelengths: blue, green, yellow, orange, and red. When that barrage of white light hits the chemical dye molecules woven into your dry red shirt, the dye acts like a highly selective mud pit.
Selective, meaning it only swallows certain ping pong balls.
Exactly. The chemical structure of a red pigment is tuned by nature, or by a chemical engineer, to absorb the shorter wavelengths of light.
Ah, okay.
So the blue, green, and yellow photons hit the pigment, and they are absorbed. They turn into a tiny bit of heat. They never leave the shirt.
But the longer wavelengths, the red ones.
The chemical structure of the dye cannot absorb them. It rejects them.
So the red ping pong balls bounce off the jagged rocks.
They scatter, yes. The red wavelengths ricochet off the pigment molecules and scatter back out into the room.
Okay, that makes sense.
And a small fraction of those scattered red photons happen to be on a trajectory that goes straight through your pupil, hits the retina at the back of your eye, and your brain translates that specific electrical signal into the concept we call red.
Okay, this is really clicking for me now. The shirt is basically a filter. It destroys the blues and greens and spits the reds back at me.
Exactly.
But I have to ask a natural listener question here, something I think a lot of people wonder when they first notice a wet spot darkening.
Go for it.
Is the water acting like a dark dye? Like, is there some kind of immediate, temporary chemical reaction happening between the tap water and the fabric's pigment that makes it suddenly absorb more colors?
It's an incredibly common assumption, but the answer is a definitive no.
Wow, okay.
Water is generally an inert solvent in this specific context. There is absolutely no chemical change happening to the dye molecules when they get wet.
So the dye itself is fine.
The pigment is doing the exact same filtering job it was doing 3 seconds before the spill. It's still rejecting the red light.
So the physical machinery of the color is completely untouched.
Completely. What you are witnessing when you spill water on yourself is a purely physical, structural, optical illusion.
That is wild.
It is entirely governed by how the light paths are being redirected before they even have a chance to properly interact with the dye.
Okay, if the color is just light bouncing back to us, and the chemical dye hasn't changed its behavior at all, that raises a massive question.
What's that?
What exactly is that light bouncing off of when it hits our dry clothing? Because, I mean, when I run my hand over my cotton P-shirt, it feels perfectly smooth. It feels like a single, solid, continuous surface.
To your hand and to your macro level perception, it is smooth. But to a photon of light which operates on the scale of nanometers, your shirt is not a flat surface. Not even close.
Really?
If we were to take your dry shirt and put it under a powerful scanning electron microscope, we would see a chaotic, mountainous landscape.
Like a microscopic mountain range?
Exactly. A dry piece of fabric is an incredibly complex, tangled network of microscopic fibers. If it's cotton, Those fibers are made of a natural polymer called cellulose.
Right, cotton is cellulose.
And importantly, those twisted fibers are interspersed with countless tiny pockets of empty space.
Basically, it's woven air.
It is mostly air. Fabric has a massive surface area to volume ratio. It is a highly porous material. You have fibers crossing over fibers, creating microscopic caverns, tunnels, and gaps.
Okay, so a dry shirt is essentially a microscopic jungle of cellulose threads and empty air gaps.
Yep.
How does our stream of incoming ping pong balls, the light, react when it hits that specific jungle?
To understand the physics of that collision, we have to introduce a crucial concept called the refractive index.
Refractive index.
It sounds like intimidating laboratory jargon, but it is actually a very simple measurement.
Okay, break it down for us.
The refractive index is just a number that describes the speed at which light travels through a specific material compared to its absolute maximum speed in a total vacuum.
Let me pause you there, because I think most of us grew up hearing about the speed of light as the ultimate, unbreakable speed limit of the universe. Are you saying light doesn't always travel at the speed of light?
I am. The famous speed of light you're thinking of, roughly 300,000 kilometers per second or 186,000 miles per second, is only the speed of light in a perfect vacuum.
Like in deep space?
Exactly, where there is absolutely no matter to get in its way. In a vacuum, we assign a refractive index of exactly 1.0.
Okay, 1.0 is the baseline. What about the air in the room around me?
The air in your office lobby is a gas. It's matter, but it's very thin and sparse. So it does slow light down, but only by a minuscule amount.
Okay, how much?
The refractive index of standard air is about 1.0003.
Wow, okay, so barely anything.
For all practical purposes, light zooms through the air from the ceiling fixture to your shirt with practically zero resistance. It's essentially still traveling at its maximum speed limit.
But then the light hits the physical material of my shirt.
Right. It hits the cellulose fibers, and cellulose is a dense, solid material. It has a much higher refractive index.
What's the number for cotton?
The refractive index of cotton cellulose is about 1.55.
That seems like a pretty significant jump from 1.0. What does a jump to 1.55 actually mean for the photon? Does it hit a brick wall?
It doesn't hit a brick wall, but it hits a massive speed bump. When the light moves from the air at 1.0 into the cotton fiber at 1.55, its speed drops by about 35% instantaneously.
35%. That is a brutal deceleration.
I like to use the analogy of a car. Imagine you are driving a car at 100 miles an hour down a perfectly smooth, freshly paved highway.
Okay, I'm with you.
That highway is the air. Suddenly, with no warning, the asphalt ends, and you hit a patch of deep, thick mud. That mud is the cellulose fiber.
Oh, that sounds dangerous.
When your tires hit that mud, two things happen. First, you violently decelerate. But second, unless you hit that mud perfectly straight on, your car is going to skid. It's going to jerk and twist to the side.
Right, because the tire that hits the mud first slows down before the other tire does, which pulls the car in that direction.
Exactly. And light does the exact same thing. When a wave of light hits a material with a different refractive index at an angle, one side of the light wave slows down before the other side.
Wait, really?
Yeah. This causes the entire path of the light to bend. This electromagnetic bending caused by a change in speed is what we call refraction.
Okay, so the car skids. The light bends. But my shirt isn't just one solid block of cellulose mud. It's a woven web of fibers and air gaps.
And that is the crucial detail. Let's build our main analogy for this deep dive. Think of that microscopic jungle of dry fabric not as a solid block, but as a complex three-dimensional maze.
Okay, a microscopic maze.
The pathways of the maze are the empty pockets of air. The walls of the maze are the twisted cotton fibers.
And because of that massive speed difference, the jump from 1.0 to 1.55, what happens at the boundary where the air meets the wall?
Because the refractive index mismatch is so large, it creates a highly reflective boundary. When there is a big speed difference, a significant portion of the light doesn't just bend into the material.
What does it do?
It crashes into the boundary and bounces right off. So the walls of this microscopic maze aren't just solid. They are coated in highly reflective mirrors.
I would actually push back slightly on calling it a standard maze, because in a normal maze, the walls are straight up and down. But you said the cotton fibers are twisted, cylindrical, and chaotic.
That's a vital correction, yeah.
Right.
It's a maze where the mirrored walls are curved, jagged, and angled randomly in every conceivable three-dimensional direction.
So let's trace the path of our white light. The light streams down from the ceiling, traveling through the air at maximum speed. It plunges into the maze of the dry shirt. What happens?
Total chaos. The light immediately crashes into the first highly reflective angled mirror wall it encounters. Because the mismatch between the air and the fiber is so stark, a large percentage of that light violently ricochets off. It bounces off that fiber, flies across a microscopic air gap, and slams into another mirrored fiber.
Is bouncing constantly.
It bounces again and again, rapidly ricocheting in a totally disorganized pinball effect.
And because these mirrors are angled every which way, the light isn't going deeper into the shirt, it's getting kicked back out.
Precisely. Within just 2 or 3 microscopic bounces, the majority of the incoming light is violently ejected straight back out of the surface of the fabric and into your eyes or scattered into the room.
This sounds incredibly fast.
Mm-hmm.
The light barely penetrates the material before it's thrown back out.
Exactly. Now, to ground this in the scientific literature, this specific type of chaotic, multi-directional bouncing inside microscopic structures was heavily analyzed by physicists in the 20th century.
Oh, there's a name for this.
Notably, researchers building upon the work of Gustav May, a German physicist who published a groundbreaking paper back in 1908. His work, and later derivatives by scientists like Craig Bohren in the 1980s, describe what we call Mie scattering.
Mie scattering. So this isn't just a generic bounce, it's a specific physical phenomenon.
Yes. Mie scattering occurs when the particles or structures doing the scattering, in this case the microscopic cotton fibers and the air gaps between them, are roughly similar in size to the actual wavelengths of the visible light hitting them.
And what makes Mie scattering so important to my red shirt?
A key feature of Mie scattering in this context is that it is relatively wavelength independent. Remember our ping pong balls, the blue, green, and red ones? Mie scattering doesn't discriminate. When it hits this massive refractive index mismatch, it scatters the blue light, the green light, and the red light back out of the maze with roughly equal brutal efficiency.
Wait, but if all the colors of light are being scattered back out together, all the colors mixed together make white light?
Exactly. The dry fabric is effectively generating a microscopic, intensely bright, diffuse white haze directly on the surface of the material.
Oh, wow.
This happens so quickly and at such a shallow depth that a massive amount of this light never even reaches the red dye molecules buried slightly deeper inside the fibers.
Let me make sure I'm wrapping my head around this. My red shirt looks red because the dye absorbs blues and greens.
Right.
But before the light can even get to the dye to be filtered, the chaotic mirrored air gaps of the fabric are taking a huge chunk of the raw white light and blasting it straight back into my eyes.
Yes, you are quite literally looking at a layer of disorganized, scattered white light sitting on top of the red pigment.
That's crazy.
That multi-directional backscattering mixes with the red light that did manage to reach the dye and bounce back.
It's like turning on a bright white flashlight and shining it at a red painting. The intense white glare washes out the color.
That's it exactly. It dilutes the overall perceived color. This surface scattering is what makes dry fabric appear lighter, brighter, and less chromatically saturated.
So the dry look is an illusion.
The dryness you see is actually just a chaotic cloud of white light shrapnel caused by the massive speed difference between the air and the cotton.
Okay, that completely recontextualizes what I'm looking at when I look at a pile of laundry. The dry shirt is a mirrored maze projecting a bright white haze. So that explains the baseline.
Yeah, that's step one.
But now, you drop the glass, the icy water splashes onto your chest. What happens to that microscopic maze the exact second the liquid hits it?
We enter the third phase of the physics, what water changes, and it happens instantly.
Right.
When the water hits the shirt, it doesn't just sit on top. Through a process called capillary action, or wicking, the water is rapidly pulled into the fabric.
Like a sponge.
It rushes into all of those microscopic gaps, tunnels, and pores that were previously occupied by the air.
It essentially floods the maze.
It displaces the air entirely, the R is pushed out, and the water takes up residence between all those twisted cellulose fibers.
So logically, this changes the optical collision we talked about earlier. Instead of the incoming light traveling from the air directly into the cotton, it's now traveling from the water into the cotton.
And this is where the magic of the refractive index comes back into play and where the illusion of the dark spot begins. Let's look at the numbers again.
Right, the baseline air is essentially 1.0. The cotton fiber is a dense 1.55. That was the massive speed bump that caused the violent scattering.
But what is the refractive index of water?
It's definitely higher than air. Water is dense.
It is. Water has a refractive index of approximately 1.33.
Oh, 1.33. That is so much closer to the cotton's 1.55 than the air was.
It's a massive shift. By substituting the air, which was 1.0, with water at 1.33, the gap between the two materials is significantly reduced.
So the speed bump shrinks.
We go from a brutal, tire-destroying speed bump to a very minor, gentle incline. Water acts as an optical bridge between the open room and the dense fiber. This phenomenon is known in optical physics as partial index matching.
Partial index matching, meaning the speeds of the two materials are starting to match up. But I really want to put some hard numbers on this because understanding the sheer scale of this change is what makes it click. Let's talk about the math behind the bounce.
To do that, we look to Augustin-Jean Fresnel, a French physicist from the early 19th century who developed what we now call the Fresnel equations.
Okay, the Fresnel equations.
These equations allow us to calculate exactly how much light will reflect off the boundary between two materials based on their refractive indices.
So if we run the Fresnel equations for our dry shirt, light going from air at 1.0 to cotton at 1.55, what does the math say?
The interface reflectance for unpolarized light at normal incidence is about 4.65%.
Meaning almost 5% of the light bounces right off the very first microscopic surface it hits before it does anything else.
Right.
Doesn't sound like a lot, but multiplied by millions of boundaries in the fabric.
Exactly. It creates a massive amount of backscatter. Now, let's run the Fresnel equations for the wet spot. The light is now transitioning from the water at 1.33 to the cotton at 1.55. What happens to the reflectance?
Well, because the speeds are closer, the skid shouldn't be as bad.
It drops precipitously. The boundary reflectance plummets to just 0.58%.
Wait, it goes from 4.65% down to 0.5%. That is a staggering 87.5% reduction in reflectivity at the boundary.
Yes. The highly reflective mirrors in our maze have essentially been deactivated.
Going back to our analogy, it's like we flooded the maze with a fluid that chemically dissolved the silver off the mirrors, turning them into clear glass windows.
That's a great way to picture it.
The walls of the maze are still there, the paths are still twisted, but the light doesn't crash and violently bounce backward anymore. It just glides right through the boundary from the water into the cellulose.
That is exactly what is happening. By reducing the speed mismatch, you drastically reduce the violent refraction and reflection that causes scattering.
So the white light is gone.
The disorganized white haze that was sitting on top of the fabric is suddenly, instantly suppressed.
I want to make a very crucial note here for you listening, because it's easy to get the wrong mental image. We need to be very clear that the material of the shirt is not being physically, structurally flattened by the water.
That is an excellent point to clarify, yeah.
The water isn't a steam iron. The microscopic mountains and valleys, the twisted fibers, they are all still physically there. The maze hasn't changed its shape.
Right.
The water has just optically smoothed things out. It has removed the stark boundary line. The extreme angles that used to force the light to turn around and bounce back to your eye are neutralized. The light still bends, but at much smaller, shallower, gentler angles now.
And this naturally leads to a question that helps prove that this is entirely a temporary physical optical effect and not a permanent change to the shirt.
Right. Why does the color return to normal when the clothing dries? I don't have to put it in the washing machine. I just have to wait an hour.
It comes down to evaporation. As the water absorbs heat from your body or the surrounding room, it changes state from a liquid to a gas.
It just floats away.
Right. It physically vacates the microscopic pockets of the fabric. And what happens when the water leaves? The ambient air immediately rushes right back in to fill the void.
The bridge collapses.
The optical bridge is destroyed. The refractive index inside the gaps drops from 1.33 back down to 1.0.
Wow.
Instantly, the clear glass windows turn back into highly reflective mirrors, the massive speed bump returns, the scattering resumes, the white haze is regenerated, and the dark spot vanishes, returning to its original bright red.
Okay, let's recap where we are in the journey of the photon. We've established that when the fabric is dry, it blasts the light back at us. When the fabric is wet, the water lowers the optical mirrors. It stops the light from immediately bouncing back.
Right.
But that brings us to the core of the mystery. Where does the light actually go, and why does that missing light make the spot look darker to my brain?
Because the light isn't being aggressively scattered backward at the surface, it is permitted, almost encouraged, to travel forward.
Okay.
The gentle, shallow angles of refraction at the water-cellulose boundary guide the photons deeper and deeper into the interior volume of the material. And once the light is inside that flooded, wet maze, two critical compounding things happen that trap it there.
The first trap makes total intuitive sense based on what we've discussed about the dye. Because the light is allowed to travel deeper into the fibers rather than just bouncing off the surface, it is taking a much longer, far more tortuous path through the actual physical matter of the shirt.
Yes. Think of it like a pinball machine. In dry fabric, the pinball is launched, it hits one bumper, and it immediately drains down the middle.
Game over.
In wet fabric, the pinball is launched, and it gets caught in the upper rails. It bounces back and forth, hitting bumper after bumper, traveling all over the board.
And in this microscopic pinball machine, every bumper is a red pigment molecule.
Exactly. Because the light is bouncing around so much deeper inside the material, it has a vastly increased statistical chance of finally colliding with one of those dye molecules.
Oh, I see.
In dry fabric, a photon might escape after 2 bounces. In wet fabric, it might bounce 10, 20, or 50 times inside the cotton fiber before it finds a way back toward the surface. And every single bounce is an opportunity for the pigment to act as the selective mud pit.
Which answers one of the most common listener questions we see on this topic. Does the wet fabric actually absorb more light?
Yes, it absolutely, quantifiably does. The chemical dye itself hasn't grown stronger, and its capacity to absorb a single photon hasn't changed. But the physical optical environment of the wet maze practically forces the photons to interact with the dye over and over again.
The longer path is the killer.
The artificially increased path length dramatically increases the total probability of absorption. The blues and greens that might have scattered safely away in dry fabric are almost guaranteed to be absorbed and turned to heat in the wet fabric.
Okay, so that's the first trap. The longer path leads to more absorption by the dye. But there's a second trap. And when I was reviewing the research notes you sent over for this second trap is where the science gets incredibly elegant.
It really does.
Because it doesn't just involve the water inside the fabric. It involves the surface of the water itself.
Yes. We've been focusing heavily on the microscopic depths, on what happens inside the fibers, but we also have to zoom back out slightly and look at the very top layer, the macroscopic boundary where the spill meets the air of the room.
The top of the puddle?
When you spill that glass of water on your shirt, the liquid doesn't just fill the internal pores. Surface tension causes a thin, continuous film of water to form, sitting over the rough fabric like a microscopically thin sheet of plastic wrap.
And despite the fabric underneath being rough, the top of that water film is relatively smooth and flat.
Yes, and this smooth air-water boundary acts like a sealing. And it's a very specific, highly restrictive kind of sealing governed by a principle called total internal reflection, or TIR.
Total internal reflection. I know I've heard that term before. Isn't that how fiber optic cables work? The ones that carry internet data across the ocean?
It is the exact same principle. Fiber optic cables use a high-index glass core surrounded by a lower-index cladding to bounce light down the tube without it escaping out the sides.
Fascinating.
But the physics of how TIR applies to wet surfaces was actually first modeled mathematically almost a century ago. A physicist named Anders Angstrom published a foundational paper on this in 1925, looking at the albedo of wet surfaces.
So this is old science.
His work was later refined in the modern era by physicists like John Lechner and Michael Dorf, who worked out the incredibly complex math of light trapped by liquid films.
So how does this fiber optic physics apply to my clumsy coffee shop spill?
Let's follow a very lucky photon of light. This photon enters the wet shirt, navigates the deep, tortuous path, bounces around the cotton fibers, and miraculously avoids being absorbed by any of the red dye molecules.
This is a true survivor.
It survives the gauntlet. Now it's heading back up toward the surface, trying to escape the shirt and reach your eye. It travels up through the water film and hits the ceiling, the boundary where the water meets the air of the room.
So now the light is trying to go in reverse. It's trying to go from a high refractive index, the water at 1.33, back out into a lower refractive index, the air at 1.0.
Right. And the laws of physics dictate that light can only successfully make that jump from a high index to a low index if it hits the boundary straight on or at a relatively steep, direct angle.
Okay, what if it doesn't?
If the light ray is coming up from the fabric and hits the water-air boundary at a wide oblique angle, it cannot escape.
The door is locked.
The door is locked. Specifically, for a water-to-air boundary, if the light hits the ceiling at an angle greater than about 48.8 degrees, which is known as the critical angle, it physically cannot pass through into the air. The physics simply do not allow it.
So what happens? Does it just stop?
No, light can never just stop unless it's absorbed. Instead, the clear water-air boundary acts as a perfect 100% efficient mirror.
Oh, wow.
The light undergoes total internal reflection. It hits the ceiling, and it is violently bounced aggressively back down into the depths of the wet fabric.
I see it. If you've ever looked at a fish tank from the side, or if you've been swimming underwater and looked up at the surface of the pool, you know this effect.
Yes.
If you look straight up, you can see the sky or the ceiling. But if you look at the surface of the water at a wide angle, way off in the distance, it looks like a solid silver mirror reflecting the bottom of the pool.
That is a brilliant, real-world example of TIR. That exact same silver mirror you see in the pool is happening microscopically all over your spilled water stain.
It truly is an inescapable optical trap. The water lets the light in easily from the top because the index matching removes the speed bumps. But then the smooth surface of the water traps the light from getting back out.
Exactly.
It's like a roach motel for photons. They check in, but they don't check out. And remember, once they are bounced back down into the fabric by that TIR ceiling, they are subjected to another brutal round of the first trap. They have to run the gauntlet of the red dye molecules all over again.
Double jeopardy.
The combination of these two things, the drastically reduced surface scattering because of index matching, and the inescapable optical trapping due to total internal reflection, is what fundamentally destroys the albedo or the overall reflectivity of the wet spot.
A massive percentage of the light that hit that spot of your shirt simply never makes it back to your eye. It is quelled by the fabric and turned to heat.
Yep.
And because far less light is reaching your retina from that specific area, your brain correctly interprets that patch of fabric as being dark.
The mystery is solved. You didn't dye the shirt darker, you just built a light prison on top of it.
It's fascinating. But there is another visual element here that I want to unpack, because I've always noticed it, but never understood it until reading these notes.
Oh, what's that?
When I spill water on a red shirt, it doesn't just look like someone took a gray pencil and shaded over it. It doesn't look dull or muddy. It actually looks like a richer, deeper, much more vivid red. The color seems stronger.
That is a very astute observation, and the physics accounts for it perfectly. In color science, we call this an increase in chromatic saturation.
I'm guessing this has to do with that white haze we talked about earlier, the me scattering.
Exactly. Let's go back to the dry fabric. The me scattering at the rough surface was reflecting all wavelengths, blue, green, red, equally. This created a desaturating, milky white haze that mixed with the red light coming from the pigment.
Right.
Think of it like taking a can of bright red paint and pouring in a cup of white paint. It makes it pastel. It dilutes the purity of the color.
But the water suppressed that white surface scattering by matching the index of the cotton.
Yes. The white paint is gone. The only light that does manage to escape the wet trap, the few photons that hit the TIR ceiling straight on and break free, have been deeply, thoroughly filtered by the red dye. They bounce through the pigment 10 times.
So by the time they escape, all the blues and greens have been brutally purged.
The emerging light has a much narrower, much more pure spectral distribution. It is almost entirely pure red wavelengths, unpolluted by surface scatter.
That makes total sense.
Experimental data actually shows that the mean chromatic saturation of a wet surface can be up to 1.43 times larger than when it is dry. You perceive a darker spot, yes, because there is less overall light. But the light you do see is a significantly purer, more vivid color.
That is so cool. Okay, before we move on to explore where else in the world this physics is secretly operating, I want to formally step in and bust two very common myths for you listening.
Good idea. Let's set the record straight.
We've laid out the real physics, so let's kill the misconceptions once and for all. Myth number 1. Clear water adds a dark color to the fabric.
We can confidently say this is false. Water is transparent. It has no pigment, no color to add. The thin films of water on your shirt do not absorb visible light in any mathematically meaningful way. The water isn't absorbing the light. The fabric is absorbing the light because the water trapped it there.
And myth number 2. The darkening happens simply because the heavy water physically flattened the fibers of the shirt down, or perhaps washed the microscopic white dust and dirt away, revealing a darker color underneath.
Also, demonstrably false. While a soaking wet shirt might physically droop on your body, the microscopic structure of the twisted cellulose fibers isn't magically flattened into a perfectly smooth sheet.
Maze is still a maze.
The physical maze remains a maze. And while washing away dust can remove some minor surface scattering, the extreme darkening effect, the 87% drop in boundary reflectance, happens even on perfectly pristine, sterile materials in a vacuum-sealed laboratory. It is purely about redirecting the paths of light.
All right, we've mastered the laundry spill. But water doesn't just turn our clothes into inescapable optical traps. The world plays this exact same trick on us everywhere, every single day. Let's look at where else this happens.
It is a universal principle of optical physics. It is not limited to cotton cellulose. Anywhere you have a rough, microscopically porous material that is wetted by a clear fluid, you are going to see these exact same mechanisms, partial index matching and total internal reflection, go to work.
So I have to ask about driving. Is this the exact same reason wet pavement looks so dark? Because when it rains heavily, the roads get so dark they are incredibly hard to see at night. The lane lines disappear, and it feels dangerous.
It is the exact same reason, and it is a massive challenge for civil engineers.
Hmm.
Asphalt and concrete might look solid and flat to us as we drive over them, but microscopically, they are incredibly porous, jagged, and rough.
Right, they're not smooth glass.
They are made of crushed sand, jagged minerals, and dark binding agents.
So they behave exactly like the cotton fabric maze.
Exactly. When rain falls and fills those microscopic crevices in the road, it replaces the air.
Hmm.
It reduces the diffuse mist scattering that usually makes dry concrete look like a bright light gray.
Wow, okay.
The water matches the index of the road, traps the ambient streetlights via the TI ceiling, and forces that light to bounce around inside the dark asphalt binder where it is aggressively absorbed. The road goes instantly black.
It also completely explains the other half of the wet road problem, the glare. The diffuse, helpful reflection of the dry road is gone, but the smooth film of water sitting on top of the road creates specular reflection, like the flat bathroom mirror.
Yep, the water film.
So the road is pitch black, but it bounces the headlights of oncoming cars directly violently into your eyes.
It's a double hazard. And it's why modern road safety engineers actually use the physics of total internal reflection to fight back.
Oh, really? How?
The reflective paint used for lane lines and those raised pavement markers you drive over are embedded with thousands of microscopic glass beads. These beads are engineered with a very specific refractive index so that when light from your headlights enters them, they use TIR to bounce the light directly backward to the driver even when submerged under a film of rain. They are fighting index matching with engineered index matching.
That is brilliant. Okay, what about out in nature? Like rocks on a beach or in a riverbed?
It's the same story. Dry pebbles on a beach often look dull, faded, and dusty, mostly a light, ashy gray or brown. This is because their surfaces are microscopically pitted and scratched, creating massive surface scattering.
But then they get wet.
But you throw those same pebbles into the surf or let a river wash over them, and suddenly they look like vibrant, polished gemstones.
The water acts as the optical bridge, hiding the scratches.
Yes. The water closely matches the refractive index of the stone's rough surface minerals, allowing the sunlight to penetrate deep past the scratches and reveal the rich, highly saturated true colors of the geology underneath.
So that's why people polish rocks.
In fact, lapidary, the art of gemstone polishing, is essentially just the process of permanently removing the surface scratches so you don't need water to see the color. You are permanently eliminating the air gaps that cause the scattering.
I notice this even happens to my own body. When I get out of the shower, my hair looks significantly darker.
Human hair is highly fibrous and rough on a micro scale. It's covered in microscopic overlapping scales like shingles on a roof.
And water just gets right in there.
Water fills the gaps under and around those scales, causes the individual strands to clump together through surface tension, reduces the air to keratin boundaries, and suppresses the scattering. Wet hair traps light, so wet hair looks darker.
But wait, this brings up an interesting variable. Why do some fabrics or materials show a much bigger wet spot than others? If I spill a glass of water on a shiny black raincoat, or even just a deep, pure black cotton t-shirt, the wet spot barely looks any different than the dry fabric. It doesn't get noticeably darker.
The material structure and the baseline color of the object are massive variables in how strong this illusion is. Let's take the glossy raincoat first.
Okay, the raincoat.
It already has a perfectly smooth, engineered surface coating. There are no microscopic, porous air gaps for the water to fill.
It's basically a solid wall.
There is no white haze of me scattering to suppress because it's already smooth. It's already doing specular reflection, so adding water doesn't change the optical physics much.
And what about the black cotton t-shirt? That has the air gaps.
And it does. The water still acts as a bridge, and the light still gets trapped by TIR. But think about the dye.
Right, it's black dye.
The dye concentration in a black shirt is so incredibly high and so efficiently designed that it is already absorbing nearly 99% of all the light that hits it, even when it's dry.
Ah, it's already swallowing all the ping pong balls.
Exactly. Index matching and trapping the light can't force the shirt to absorb much more light because it's already operating at maximum absorption capacity.
You can't get darker than black.
You can't make something much darker than pitch black. So the visual difference between dry black and wet black is minimal to the human eye.
So to see a really dramatic wet spot, you need a highly porous light to medium colored fabric, like my bright red shirt or a pair of khaki pants.
Right. Khaki is notoriously bad for showing spills because the baseline scattering is so high and the dye is relatively weak, so the contrast when it gets wet is huge.
Makes sense.
But there's one extreme exception to this rule that is absolutely fascinating. What happens if you apply this physics to a material that is highly porous but has almost no dye to absorb the light at all?
Like a really thin, cheap white cotton t-shirt.
Or a standard piece of white printer paper. White cotton or paper has no pigment. The reason it looks white is purely because of that massive slattering we discussed.
All the light bounces back.
The air gaps are bouncing 100% of the white light back at you. So when you wet a white shirt, the water bridges the gap. It suppresses the surface scattering and forces the light to travel forward into the material, just like before.
But there's no red dye to trap it. There's no mud pit.
Exactly. Because there is no dye to absorb the photons, the forward-directed light isn't turned into heat. It just keeps bouncing forward, eventually passing right out the other side of the fabric.
The ping pong balls just blast straight through the maze and out the back wall.
This is a phenomenon specifically called optical clearing. It perfectly explains why white, wet shirts, or wet paper, become highly translucent or even transparent, rather than just dark.
The light passes right through.
The light isn't bouncing back to you, so the wet spot looks darker than the dry shirt. But if you hold a wet piece of paper up to the light, the wet spot is actually brighter than the dry paper, because it's transmitting the light straight through the material and into your eye.
There is an amazing classic physics experiment detailed in the research that proves this index matching concept perfectly. And I want to share it because it completely visualizes the math we've been talking about.
Oh, the sand experiment.
Yes. In a study validating all this, researchers took a pile of dry, white quartz sand.
Sand is a perfect test subject. It's highly porous, jagged, and heavily scatters light, which is why a pile of sand looks opaque and white.
Right. And quartz sand has a specific refractive index of about 1.54. The researchers wetted this sand with different liquids of increasing refractive indices to see what would happen to the light.
This is a beautiful, elegant demonstration of the physics at play.
First, they used standard water, which is 1.33. As expected, the gap went from 1.0 to 1.33, and the white sand got moderately darker, like wet sand on a beach.
A classic wet sand look.
Then, they stepped it up. They used glycerin, which is a thick, clear liquid with a refractive index of 1.47. 1.47 is getting much closer to the sand's 1.54.
The optical bridge is getting stronger. The speed bumps are getting smaller.
And the result was that the sand got heavily darkened and noticeably translucent. The scattering was almost gone. But then for the final test, they poured a clear chemical called benzyl alcohol into the dry sand.
And this is the punchline. Benzyl alcohol has a refractive index of exactly 1.54. It is a perfect mathematical match for the quartz sand.
A perfect match. So the relative index between the liquid and the sand became exactly 1.0. There was zero speed bump.
None at all.
There was zero optical boundary. To a photon of light, there was no difference between the liquid and the solid rock. The light traveled through the wet sand without bending, skidding, or scattering at all.
And the visual result?
The sand didn't just get dark. The pile of solid quartz sand basically became completely invisible.
It's amazing.
It looked like a beaker of clear liquid. The scattering dropped to zero.
It perfectly validates the theory. The darkness, the scattering, the opacity, it is all entirely dependent on closing that refractive index gap. When you match the index perfectly, the material's physical boundaries visually vanish.
That is just incredible. The rocks are still there. You can reach in and feel them, but your eyes cannot see them because the light refuses to acknowledge them.
It's like magic, but it's just physics.
Okay, we have covered a massive amount of ground today, zooming all the way from the macro world of spilling a drink in a lobby down into the microscopic behavior of single photons skidding off cellulose and getting trapped by liquid ceilings. Well, let's bring this deep dive to a close and summarize this optical journey.
I always find this topic to be a great reminder that our intuition about how the physical world works is often completely inverted from reality. We think we see objects, but we only see the light that objects reject.
So to concisely recap and directly answer our title question for you, wet clothes usually look darker because water acts as a literal physical bridge for light.
A bridge over the speed bumps.
By displacing the microscopic pockets of air, water dramatically changes how light moves through and escapes from the fabric. It stops the raw white light from bouncing immediately back to your eye. It forces the light deeper into the material. It traps it inside using a reflective liquid sealing,
And it drastically increases the amount of light that is absorbed and destroyed by the fabric's dyes.
ultimately causing far, far less light to return to your eyes.
And because significantly less light reaches your retina, your brain flawlessly and correctly interprets that specific patch of fabric as being dark.
It is such a complex, beautiful mathematical chain of events for something that happens in a fraction of a second when you knock over a glass.
Yeah.
And so, as we wrap up, we want to leave you with a positive why stuff happens send-off. And true to form, we want to give you something provocative to mull over.
Let's talk about the cutting edge of what we can do with this knowledge. Because matching the refractive index isn't just about making sand invisible or explaining laundry. It is currently revolutionizing biology and medicine.
Oh, this is fascinating. You're talking about tissue clearing.
Yes, human tissue, skin, muscle, organs, it's just like that white t-shirt. It's a complex, rough matrix of proteins, fats, and fluids that scatter light heavily, which is why our bodies are opaque.
We can't see our own bones.
Right, we can't see through our own skin. But biomedical engineers are using the exact same physics we discussed today to change that. By injecting specific biocompatible clearing fluids into tissues, fluids specifically engineered to match the refractive index of cellular proteins, they are successfully suppressing the me-scattering of human and animal tissue.
Which means the light stops bouncing off the surface of the skin and travels straight through.
Exactly. Recent studies have actually used simple molecules, even things as common as tartrazine, which is the yellow food dye found in Doritos.
Hey, really? Doritos dye?
Yeah, they use it to temporarily match the refractive index of the fluids in living mouse skin. And when they do that, the skin literally becomes transparent.
That is wild.
You can see the blood vessels, the internal organs, the neurons firing all without a single scalpel. And when they wash the dye away, the air and normal fluids return, the index mismatch returns, and the skin becomes opaque again, just like your shirt drying out.
That is mind-blowing. The exact same physics that ruins your outfit before a meeting might one day allow a doctor to look directly into your body without surgery just by applying a liquid that turns the microscopic mirrors into clear glass windows.
All connected.
The universe is governed by profound, elegant rules, and they aren't just happening in supercolliders or deep space. They are happening right on your lap.
The physics is everywhere waiting to be noticed.
Exactly. So the next time you accidentally spill a drink on yourself right before a big moment, or you step out onto a dark, glaring, rain-soaked street, don't just see a mess or a gloomy day.
See the science.
Take a breath, look at the dark spot, and realize that you are witnessing a real-time, brilliant, multi-layered demonstration of optical physics unfolding right in front of your eyes. And who knows, maybe explaining refractive index matching and transparent mice is exactly the distraction you need to break the ice in that meeting anyway. Thanks for diving deep with us.